Hey guys, Mr. Zanak is here. Today we're going to talk about the differences between distance and displacement. Let's take a look. Assume for a second that we're going to go for a bike ride in the city. And so you go 15 kilometers to the east and then 8 kilometers south, turn right again and go 15 kilometers to the west. So the question that I have for you is, how far did you actually go? Take a moment, hit pause, and think about this. Alright, so it's kind of actually a trick question. And really what I'm trying to do is draw out the distinction here between what distance and displacement actually is. So if you looked at it from the path that you traveled, you were actually calculating your total distance of 38 kilometers. 15, 8, and then another 15 will get you to where you finished up. And that would be your distance, the total distance that you traveled. However, from a displacement standpoint, you actually only ended up 8 kilometers away from where you started and in the direction due south. And this really is the difference here. Displacement is going to be where you finished or where you ended up relative to where you started and include the direction of the distance that you traveled. Let's look at another example here. So in this case, let's say we went mountain biking through the woods, and the red path that you see is 11 kilometers through the woods, and it winds as the path goes. So the total distance that you traveled on this path is 11 kilometers. However, your displacement, again, where you ended up versus where you started, is only 6 kilometers to the north. So from a definition standpoint, distance is going to be the total length traveled along the path that you actually took, whereas displacement is going to be the straight line distance from where you started to where you ended up, your final position relative to your initial position, and you need to include the direction. That's a key element of what displacement is, and it makes it what we call vector quantity, which we'll be talking a little bit more about in a second. So let's break displacement down a little bit further, okay? So again, it's really your change in position. It's your final position minus your initial position. And one of the letters that we use is x, okay? X is going to represent your position. Now that little triangle in front of the x here is actually going to be the Greek symbol delta, and it really just means change in. And we're going to be using that a lot this year in physics. So anytime you see a delta and then another variable, in this case x representing position, it's always going to be change in. And it always is the final minus the initial. So in this case, we're talking about the final position, which is just x, minus x sub naught. And that naught is going to be representative. It's another Greek symbol. Lowercase naught is really meaning initial. Okay, so it is final minus initial position, or delta x, which really is displacement or your change in position. The base SI units are going to be meters, which will be represented by an M. And a key element here again, magnitude and direction. This is what a vector is. Okay, something, any quantity, that has a magnitude and a direction. And that's really the key difference between displacement and distance. And displacement can be both positive or negative depending on your frame of reference or your coordinate system and how you're defining position. We're going to talk about that as well. So, class, please understand that distance is not the same as displacement. Okay? Let's take a look at coordinate systems, or what's often referred to as a frame of reference. Okay, the first one that you see here is a directional coordinate system called the Cartesian coordinates. And this is what you're familiar with in math, right? You have 4 different quadrants, positive x's to the right, negative x's to the left. The origin is right in the middle. It's your 0, 0, and again, positive y up and negative y down in this Cartesian coordinate system. There's a relative directional system as well. Okay, so to the right, from your vantage point, would be positive. To the left would be negative. And these are absolute frames of reference that we're going to use to get started with so that we can all be on the same page. For example, right now, if I point to my right, it looks from your vantage point or your frame of reference that I'm pointing to your left. Okay? Up is always going to be positive and down is going to be negative as a frame of reference that we're all going to start with. These frames of reference can change and become relative to the direction of acceleration, but we'll get into that later. But for right now, up is going to be positive and down will be negative. We also have the cardinal direction system, okay? East, northeast, west, and south. So north is not up. Think about this from you're looking at a map or as you're walking or traversing around the earth, okay? So north is going to be a forward direction, south is going to be behind you, and east would be to your right, and west would be to your left. So up is positive, north is forward. Again, different ways of describing things and just making sure that we're all on the same page and having frames of reference. We'll talk more about this as we get into speed, velocity, and acceleration. So we have this distinction here between what are scalar and vector quantities. So a scalar quantity is a quantity that only has a magnitude. It can only get bigger or smaller, such as an example would be distance, speed, or time. For example, if I told you that I went 11 kilometers, you really wouldn't know where I started, where I ended up. You just know that I traveled 11 kilometers. Did I go 11 kilometers away from where I started? Did I go 5.5 kilometers away and then turn around and come 5.5 kilometers back? You really don't know, but you know how much travel was involved. Whereas a vector quantity is going to have both a magnitude and a direction. So those would be displacement, velocity, acceleration, force, momentum. Much of all the things that we're going to be dealing with are actually going to be vector quantities where we're going to need to pay attention to the direction, and it is a function of where did I start and where did I finish. And if we think back to the mountain bike, it really doesn't matter what path I take. It really matters where did I end up versus where did I start, and that's really where the vector, in terms of position, vector quantity is going to come into play. Again, we're talking about magnitude and direction. Let's take another look at an example here. Let's suppose that these two students, they're leaving their math class and they actually have to go down to the music room to pick up something before they head to their physics classroom. Okay, so what was the distance that these two students traveled? And what would be their displacement? So again, pause the video and try and solve those. Okay, so from a distance standpoint, it's actually going to be 15 meters. 6 meters to go from the math to the music classroom, and then 9 meters from music down to physics room. That's the total length that they traveled, 15 meters. But what was their displacement? Their change in position from the whole trip, starting at the math room and ending at the physics room. It's actually -3 meters. And that -3 meters just means 3 meters to the left in this frame of reference, with the positive x direction being to the right. Again, your frame of reference is really important when you start to talk about position and direction of vectors, so you really need to pay attention to that. So let's recap. Did you learn the differences between distance and displacement? Could you describe the differences between a scalar and vector quantities? Do you know that displacement is a vector with both a magnitude and a direction, and that vectors can be both positive or negative, and that you'd be able to describe position with different directions and coordinate systems? See you soon.